Good day, I'm Norman Wobblinger. This new point of view that we're developing towards linear algebra and matrix theory also gives us new insight into the nature of vectors. That's what we're going to be talking about today. So we're going to revisit this subject that we originally talked about in Math Foundations 30, quite a long time ago, a video called What Exactly is a Vector? And we're going to look at this very important central kind of notion in a new way. So back then we had a very geometrical point of view, talking about a plane, points represented with square brackets, like this point here, this is 1, 1, this is 3, 2, and then this line segment joining A to B. We can think of that as actually just an ordered pair of points. It really only depends on A and B, so that's one way of thinking about it. That's how we thought about vectors back then. And when we want to work algebraically, we take the difference between the coordinates of the points to arrive at this vector 2, 1, 2 over in the x direction, 1 up in the y direction. So it's a measure of a relative position between 2 points. So this is a very nice geometrical approach to vectors, and it leads to algebraic operations with vectors, such as taking addition of vectors or scalar multiples of vectors, or more generally taking linear combinations. So for example, if v is the vector 2, 1 and u is the vector minus 1, 4, then we can create something like 3v plus 2u, 3, 2, 1 plus 2 minus 1, 4, to get the vector 4, 11, just working component-wise. So in this video today, we want to have another look at this story motivated by our understanding about data structures. We have now more sensitivity about building things up and how we actually concretely can construct things from simpler things by putting them in the appropriate kinds of boxes or data structures. And we're going to see that a new kind of object emerges, a very central object called a vexel. Vexels are the one-dimensional analog of maxils. All right, so one approach to vectors from a maxil point of view is to think of vectors as being sort of maxils with just one row or perhaps one column. So the two vectors that we were considering could be thought of in terms of maxils this way. V could be the maxil 2, 1, and U could be the maxil minus 1, 4. In order for that to work, obviously we have to extend our notion of multiset, because previously we were thinking of a maxil as being a multiset of pixels, and the multiplicities involved in that multiset had to be natural numbers or a zero. Okay, but we've seen that in certain circumstances it's natural and useful to extend the multiplicities that objects are allowed to have in a multiset to also include negative numbers. If we do that, then we can regard this thing here as something that's not so shocking. It's minus 1 times the maxil E11 plus 4 times the maxil E12. V here is 2E11 plus E12. And then we could take linear combinations of things like this just in the context of M-set operations, because that's what we're really doing. So we could take 3 times this one plus 2 times this one, and we would algebraically work out that that's 4E11 plus 1112. Or 5V minus U, we could also take that kind of linear combination. 5 times this one minus one of these, and again we just work with the E11s and the E12s separately. So there's 10 of them here and plus 1, that'd be 11 E11s altogether, and there's 5 E12s here, and we're subtracting 4 E12s for a total of plus 1 E12. Okay, so this is something we could do. We could regard vectors as just maxils supported on one row or column. While tempting to do this, it turns out, in my opinion, that we should not do this. Okay, this is not really the right way of thinking about vectors. There is a more fundamental, better way of proceeding. So here are 3 reasons why we might not want to go in that direction. The first is that there's a question about which row or column we should be considering as the row or column associated to the notion of vectors. So suppose we have a traditional matrix vector equation like this. So this is a kind of equation involving a 2 by 2 matrix, a vector, and the product of this matrix and this vector is this vector here. I remind you it's 3 times 1 plus 4 times 5, which is 23, and 1 times 1 plus 2 times 5, that's 11. Now, this sort of traditional matrix vector equation can be interpreted in our Maxwell point of view this way. So we could replace this matrix with this Maxwell. We could replace this matrix with this Maxwell, and then the product of these two Maxwells is indeed this Maxwell here. So that's one Maxwell interpretation of this. But another Maxwell interpretation of essentially the same equation is this one here, where we're taking that same 2 by 2 matrix and writing down a Maxwell there, but now this vector here gets interpreted as being the Maxwell with elements in the second column, so 0, 1, 0, 5. And now when we do the multiplication of these two Maxwells, we get this one here. So what's happening here is that the vectors over here are being replaced with the second columns over here, as opposed to the first columns over here. So there's then this ambiguity. Should one choose the first row or the second row or the 15th row, or the first column or the third column or the 319th column? Okay, so that's one issue. Another issue is that we would then need to distinguish between row vectors and column vectors all the time. Because, well, if we're talking about rows or columns as vectors, we have to decide which of the two we're actually talking about in any given situation. And the third reason is that it's unsatisfactory, really, to have a one-dimensional concept, that of a vector, dependent on a two-dimensional concept, that of Maxwell. We may be motivated that way in terms of how the topic arose, but logically it makes more sense if we start with the one-dimensional thing as being simpler, and then the two-dimensional story is a more complicated or enlarged version of the one-dimensional story, and then so on. All right, so on this slide here, I'm really presenting quite a new way of thinking about things. And if you're a professional mathematician or a graduate student, don't be fooled by the seeming simplicity of things here, right? This is really a major new way of thinking about things, and it will take some time. It may take several weeks or even months for this to sink in. So just let it sit there for a little while and don't hurry it. Okay, it's very simple though. So the main new concept, that of a singleton and a vexel. So a singleton is a one list from natural numbers. For example, here is a one list from natural numbers. A equals 1. There's a natural number. There's a list with one element. That element is from the natural numbers. Here's another one. B equals 37. It's a list with one natural number in it. So this is very much like what a pixel is. A pixel was a 2 list from natural numbers. So this is some kind of simpler, more elementary version. Instead of having a 2 list from natural numbers, that's a pixel. Now we have a 1 list from natural numbers, and we're going to call that a singleton. So notice that a singleton, like A equals n, square brackets n, it is really a different mathematical object from the natural number n. There's the natural number 37, and there's the singleton, square brackets 37. And they are two very different things. Okay? The singleton in particular is a list, while 37 is a number. So we're going to introduce a type, let's say sing for singleton. And this is really just the type that otherwise we might write this way, list nat1. It's a one list from natural numbers. It's a list with one element. That element comes from or has type natural numbers. Okay, so a singleton is an analog of a pixel. What did we do with Maxwell theory? Well, we took pixels and we created multisets of them, and we called them Maxwells. So we're going to do exactly the same thing here. We're going to say that a vexel now is a multiset of singletons. A vexel is a multiset of singletons. Here, for example, is a vexel. It's a multiset. Inside it, there's a singleton, there's another singleton, there's another singleton. There's no commas, so it's unordered. And repetitions are allowed, as evidenced by the square brackets. It's a multiset of singletons. Here's another multiset of singletons, another vexel. 1, 2, 4, 1, 1, 2. And I remind you the order here is unimportant. We can move them around. And we're going to have a new name for this new type, vex. And we could say that that's also an M set from sing. It's an M set whose objects are all singletons. Okay, this is an important kind of new type of object. I mean, it's not as if people have not been considering these things before, but the important thing here is that we're putting our finger on it and saying this is an important concept. Right? This is a very fundamental building block for mathematics. We're going to give it a name. We're going to give it a type. We're going to put it center place in our theory of linear algebra. We're going to see that it structures lots of things for us. In particular, it employs multiset theory to help us build up essentially linear spaces. Multisets are great objects, and we're exploiting the fact that we can work with multisets here, or M sets. Exactly the same kinds of considerations that we saw for maxwells are going to be happening here with these vexels. So vexels are M sets, so we can add them. We can take multiples. We can take linear combinations. And in addition to those sort of linear space operations, we can also take unions and intersections, just as we did for maxwells. So here is V, and here is U, the same ones we had before. Then V plus U is just the M set that we get, as usual, just by dumping the two M sets together into a collective box. So there's now a 1, 1 from there, and there's a 1, 1, 1 from there, there's a 2, 2 from here, there's a 3 from here, and there's a 4 from there. We can take the intersection, so we're looking at minimums of multiplicities. We can take the union, we're talking about maximums of multiplicities. We can define one vexels, same kind of thing that we did with maxwells. We can identify that when we just have a single natural number, say n, inside, there's the singleton n, and then this thing here is the vexel containing that single singleton. We can call that E sub n. So E sub 1 is this one, E sub 2 is this one, and so on. These are all vexels. They are particular kinds of vexels. They are sort of like basis vexels, if you like. They are sort of building blocks. So arbitrary other vexels, like this one here, can be written as linear combinations of these vexels. So this one here is 2e1 plus e3, and this one is 3e1 plus 2e2 plus e4. And then when we take a linear combination like 5v plus 4u, we can do it at the level of these linear things here. So we can just say, well, 5 times this one and 4 times this one. We can make a computation how many e1s there are. There's 10 and 12, so 22 e1s. How many e2s there will be? There will be 8 of them. How many e3s? We have to multiply that by 5. And how many e4s? We have to multiply that by 4. So we can express linear combinations in the usual kind of linear algebra way, regarding these kind of as basis elements. But they're just names for particularly simple types of vexels. So very analogous to the Maxwell situation, but in some sense simpler and probably more fundamental. When we were developing Maxwell theory, what we did is we said, okay, we have an M set of pixels. What we can do is we can record the various multiplicities by putting them on a screen. Basically creating a sort of a list or a two-dimensional list of multiplicities that corresponds to the M set. So we have an M set over here, and we associate to it a list of multiplicities. And that was basically our picture of a Maxwell. So we can do exactly the same kind of thing here, but we need to first create a one-dimensional analog of a screen. Now there's at least two possibilities here, and we're going to call them friezes. So a frieze is a one-dimensional version of the screen. This is a kind of a classical term used in architecture. If you have some building and maybe there's a strip near the top, with sort of essentially a one-dimensional strip, often with sculptures on it, so that would have been called a frieze in sort of classical architecture. So that's what a frieze means. It's essentially a one-dimensional array of objects. The objects aren't necessarily exactly one-dimensional. They can have some extent, but there's really a sort of a one-dimensional family of them. Object, 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 all in a row. So there's two kinds of friezes which sort of naturally occur to us here. We could create a one-dimensional strip like this and call it the row frieze, where we have positions marked corresponding to the singletons. 1, singleton 2, singleton 3, singleton 4, etc. Or we could have a column frieze, where we have a column, basically a one-dimensional ribbon or strip going down, with positions marked for the singletons 1, 2, 3, 4, and so on. So now given a vexel, V, which is an M set of singletons, we could represent that vexel as a picture. We could basically record how many 1s there are, how many 2s there are, how many 3s there are, and record those numbers as multiplicities on our frieze. So we could write V equals 201 if we were using the row frieze framework, or if we were interested in the column frieze framework, we would write 201, representing 2 1s, 0 2s, 1 3, and 0 4s. So just as for maxils, there's something open-ended about these frieze diagrams in the sense that we could add zeros. If we added another 0 here, it's not going to change the underlying M set. So the primary object is definitely this thing here. This is actually the vexel. Okay? These are pictures or representations of the vexel. And we see that we have a choice of pictures here. Well, even in the maxil world, we could have had lots of choices. When we chose to arrange our screen so that the sort of 1-1 entry was in the top left. That was a rather arbitrary choice. Okay, so but here we want to really incorporate the idea that there's a symmetry between rows and columns. It's going to be very important. We don't want to say that the rows are more or less important than the columns. We want to have a kind of balance between rows and columns. It's a very important symmetry in this story. So we're going to introduce row frieze, column frieze sort of simultaneously, and we're not going to say that one of them is more important than the other. So both of these are representations of this vexel right here. Now, those of you who've been watching the series for some time will, I hope, sort of say, wait a minute, we've seen something like this before. We've seen very much this kind of story before when we were talking about polynomials, what we called polynumbers. The way we introduced polynumbers was very much like this. In fact, we had a similar kind of story. We had polynumbers sort of going down, and we had polynumbers going across, and they played somewhat different roles. So, yes, it's true that what we're doing here is going to connect very directly with polynumbers, and we will get back to that. All right? So, we'll keep that in our minds. The understanding that we're gaining here will be useful in other situations as well. So we have vexels, and now we have this idea of a frieze, which is the one-dimensional analog of a screen, and we have this idea of representing a vexel with a multiplicity list, essentially, a diagram visualized on our frieze. And so now where does a vector fit into this story? Well, a vector plays a very analogous role to that of a matrix. Once we have maxils, then we saw that a matrix could be thought of as a picture of a maxil. So what you get when you have a maxil and you decide to put it in a frame, in a box, you want to take a picture of it. So you bound it not just by its natural boundaries, but also some by arbitrary other boundaries there, and you get a rectangle and say that is now a matrix. But it's a little bit arbitrary. So exactly the same thing is happening here. So a vector, for us now, can be thought of as just a picture of a vexel. So here's our vexel V, 1, 1, 3. And we saw we had two different ways of representing that on a frieze, either a row frieze or column frieze. And then associated to that, we could take a picture of that representation. So in terms of the row frieze, we could take the coefficients 2, 0, 3 and put brackets around them. Just identify them, sort of truncate the rest, and say, ah, look, there's a vector. This vector corresponds to this vexel. Fair enough. Or you could alternatively come along and say, well, we want to think about a column freeze. We're going to choose this vector, 2, 0, 3, as representing the same vexel. So the vexel v can be associated, or is associated to a row vector, this one here, or perhaps to a column vector. So in mathematics, there's a lot of ambiguity, perhaps even confusion, about the role of vectors. Okay, so there's various concepts which get intermingled in a not entirely straightforward fashion. So there's notions of vectors, and then a little while later you find out there's things called row vectors and column vectors. And sometimes they're sort of the same, and sometimes they're quite different. And then on other occasions you think of vectors as being just special kinds of matrices. Okay, so sometimes matrices and vectors are different beasts, and sometimes vectors are just special cases of matrices. So we say that a vector is like an n by 1 matrix or a 1 by n matrix. And then of course we have this idea of Rn, where we employ this red herring of the real number system, which is completely beyond what we're doing here, right? Complete and utter fantasy talking about Rn. Okay, even though the linear algebra books are all full of things like this. So when they talk about vectors like this, they talk about R3, that this is a vector in R3. It's complete fantasy, right? Obviously, there's integers here, not real numbers. If there were real numbers, then these entries would go on infinitely, and there's no chance you'd have at all of writing them down. Okay, so we say Rn, but in fact, 99% of the time we write down and think about integral examples or perhaps rational examples. It's a big cheat. In any case, there's some confusion, and there's a kind of a flexibility and an unwillingness to pin down exactly what the words mean. All right? So for us, our orientation is going to be that the vexel is really the primary concept here. That's really at the heart of the story at a foundational level. Okay, that's a very powerful point of view. So from this point of view, we're going to replace the usual idea of this hierarchy of linear spaces, which permeates modern linear algebra. The idea that there's a one-dimensional space of vectors, there's a two-dimensional space of vectors, there's a three-dimensional space of vectors, and so on. V1, V2, V3, or maybe R1, R2, R3, etc. This is a hierarchy. So we're going to replace this idea with the idea that there's really just a single realm of vexels that encompasses all of these vectors really at the same time. So these are all just sort of slices or views or partial visions of this bigger picture. So for example, here's a vector W, 5, 1, 3, 2, traditionally written down. Here's another vector U, 1, 2, traditionally written down. So in most linear algebra treatments, these are thought of as living in quite separate spaces. This is living in a four-dimensional space somewhere, this is living in a two-dimensional space somewhere, and they don't really mix. They're quite different creatures. But for us, these are just pictures of the actual underlying fundamental objects, which are data structures. So this W is really this M set of singletons. The 5 represents that there's 5 singleton 1s, 1 represents there's 1 singleton 2, then there are 3 singleton 3s, and there are 2 singleton 4s. This really is the M set that's represented from this data structure point of view by this vector. And this vector here represents this M set, 1, 2, 2. That's an M set. That's an M set. They're all living in the world of M sets of these singletons. In particular, we can add them. We can take linear combinations. We can do lots of things with these M sets at the same time. We don't have to keep them separate. We can see that there's a difference between this one and this one in terms of their supports. This one is supported on the 1s and the 2s. This one's supported on 1, 2, 3, 4, so the supports are different. But algebraically, they're still part of this same story. So the M-set point of view is very, very powerful. We are going to be interested in vexels for a number of reasons, but one very immediate reason is because we want to study the idea of the rank of a maxil. So it turns out that a maxil M has associated to it a distinguished number. It's the most important number associated to a maxil. So if you're given a maxil M, almost the first question that you should ask about it, other than sort of roughly, where is it, is what is its rank? So the rank of the maxil, we'll denote it rank M, is a natural number or possibly 0. The definition is somewhat subtle, and to set it up, we are going to use vexels. So the idea of a vexel is a tool that we're going to use to explore maxils. So here's roughly the story of what we're going to do. So here's a maxil. Okay, it's seemingly arbitrary maxil. It turns out that this maxil has rank 3. That's not at all obvious if you just look at it. It turns out that if a maxil has this shape, then the maximum rank it could have is 4. But this does not have rank 4, it happens to have rank 3. And that says a lot about the maxil. It's a very important concept in linear algebra. Okay, so to get at this notion of rank, so I'm going to explain this in my next video, but to get at it, we are going to be looking at associated vexels. So what we're going to do is we're going to look at rows of this maxil. For example, this third row right here. See that third row, 7, 4, 25, 23? We're going to think about taking those entries and sort of peeling them off to create a one-dimensional version of a maxil, namely a vexel. Right. And the vexel is 7, 4, 25, 23. And we're going to say that this is the third row of the maxil M. So the third row of maxil M is this vexel. And correspondingly, if we say take the second column, that'll be C2. C2 of M, it's the second column of M, will be this vexel. So here the vexel occurs as a row vexel, and here the vexel occurs as a column vexel. Okay, but basically this is the idea that we want to think about rows of these maxils, but we want to think of those rows as really living in this one-dimensional kind of world of vexels, rather than as special types of maxils in this two-dimensional situation. Because ultimately we want to compare this row with this row. We want to talk about linear combinations of rows or of columns, and to do that it's most convenient if we work in this really truly sort of one-dimensional story contained in the world of vexels. Okay, so that's roughly where we're going to go in our next video, where we're going to carry on talking about the rank of a matrix and the role of vexels in understanding that very important notion. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.